Okay, welcome everyone. A few people are still arriving. Anyone have any questions, thoughts, stories to share while we're waiting a minute or two for everyone to get zoomed in? So let me just remind you my preferences, if at all possible, to please share your screen. It's great to see people actually looking back at me. Okay, so if not, let's get started. So my plan for today is to do the Hopf argument for the hyperbolic automorphisms of a torus, and then begin the study of hyperbolic geometry, especially hyperbolic surfaces, which will be the setting for more advanced ergodic theory. Let me point out that Carl Windsor, our course assistant, TA, has kindly written solutions to the homework. They're posted to the webpage for those of you who are doing the homework, or even if not. The problems were pretty interesting, and these will be forthcoming, of course, in the future. I should remark that the homeworks are numbered by the week they were assigned. So the first homework is called homework 2, since there was no homework on week 1. Okay, so we're going to discuss this Hopf approach to ergodicity and mixing on the torus. But first, let me talk about something much simpler, which is a translation flow on the torus. We haven't done much with flows in this course, but they're very similar to iterating a single transformation. So we pick a vector E in R2 not equal to 0, and we consider the flow on the torus, ht from x to x, given by just translation by this vector E. So you can think of E as being in the tangent space to the torus, or which is trivialized by translation. So this is the flow that simply you have a parallel vector field at every point, and then given a point and a time t, you flow along that vector field for time t. If t has modulus 1, then you just move distance t on the torus. It's a unit speed flow. And when we're studying flows like this, if we have, say, a function f in L2 of the torus, or a function f that's continuous on the torus, etc., then to do averaging, we have to do integrals rather than sums. So the corresponding averaging operator, st of fx, is obtained by flowing forward and back for time t, and then integrating the result. So you look at the values of f at hs of x ds. So what that means is you just average the values of s over both the forward and backward flows of h for time t, and make that your new value at x. Okay, so now this flow should remind you of something we've studied a lot, which is just translation in an abelian group. After all, X is an abelian group, and we're just translating by group element. Actually, we're translating by all the elements in a one-parameter subgroup of X, namely the one-parameter subgroup generated by E. And just as for a translation by a single element of an abelian group, the theorem here is that HT is uniquely ergodic, and in particular ergodic, that will be all we need for the subsequent discussion, if and only if, well, let me put it this way, it's uniquely ergodic or periodic. In other words, if we look at the subgroup R dot E, and we take its closure sitting inside of X, there's two possibilities. One is that this subgroup is equal to a circle. It's a copy of a circle inside of the torus, and that's because you're flowing at a rational angle and you eventually come back to where you started. Otherwise, you're flowing at an irrational angle, and the closure then, being a Lie subgroup, has to be the whole of the space X. And in this latter case, as usual, any HT invariant measure is also invariant under translation by elements in this closure, and there's a unique translation invariant measure on any abelian Lie group, it's Haar measure, so HT is uniquely ergodic. And so in particular, we didn't prove the version of the ergodic theorem for flows, but it's what you would expect. If we're in the ergodic case, then the subs tend to the integral over x of f. And if you like, they converge in L2. We start with something in L2. That's the von Neumann theorem. And they also converge AE if f is in L2, if f is continuous, even if f is, if it's one-to-one. Unique ergodicity assures that if f is continuous, then it actually converges uniformly. But we won't need that for the subsequent argument. Okay, so that was a little preliminary, and the really interesting thing about toral automorphisms, this is what Hopf exploited, is that a discrete automorphism of the torus has an associated flow when the automorphism is hyperbolic. Namely, it has these two foliations that we drew last time. So now let T and SL2Z say be hyperbolic. And I'll also write by T the associated map. Remember, the way you can think of this is just that a 2x2 matrix gives you an action on R2. And on this R2, the universal cover of X, since it has integral entries, it gives an automorphism of a lattice. And so it descends to an automorphism of the function space. And and by hyperbolic, I mean that its eigenvalues are outside the unit circle. And so they're of the form lambda and 1 over lambda. Just for convenience, I'm going to assume that lambda is greater than 1. It could be also less than -1. Okay, and so we then have to analyze this transformation. Well, we're going to prove the following theorem, which we already know, that T is mixing. But we're going to prove it using the foliations produced by T. In particular, we're going to use an eigenvector. So we choose an eigenvector E, it's unique up to scale, such that TE is lambda E. It's the expanding eigenvector. As you iterate T, this eigenvector gets longer and longer. And here's our idea. The idea is that if we take a ball around the origin and we apply T to it many times, well, two things happen. First, we have expansion in the direction of E, and then there's a complementary eigenvector, and we have contraction by 1 over lambda in that direction. So the image of the ball becomes a very long ellipse. And it's along this flow line of HT. So that means averaging over a high inward of this ball is very similar to averaging along a long leaf of the expanding foliation or a long orbit of HT. Oh, but averaging along a long orbit of HT just converges to the average over all of the torus. And so that proves T is mixing. When you take a ball, a large inward of it approximates a long orbit of this irrational flow, and then you're done. So, of course, we need to know the flow is not periodic, but that's obvious because of the fact that the integral lattice is preserved. If to be periodic would mean that this eigenvector passes through an integral point, and then this integral point, would have to be mapped to itself, since it's on this eigenline is mapped to itself, and that's incompatible with this expansion. Another way to put it is, if this were periodic, we would get a closed loop on our torus. Here, we get this closed loop, and then T would map that closed loop to itself, but it's supposed to be expanding by a factor of lambda, so that doesn't make sense. Okay, so we're going to use this eigenvector, and then we're going to use the interaction between T and the corresponding flow, HT. And this is one of the biggest ideas in dynamics, is we're starting with T, and then we're finding another, we're going to analyze T by enriching the set of dynamical systems we study. And so you might ask, what if you take this flow HT and you take this transformation T and you take the group they generate as mappings of the torus to itself? What do you get? Well, the nice thing is that T and HT interact in a very simple way. So that's of such signal importance that I'll write it down over here. So I claim that T of HT is equal to H lambda T composed of T. And that's because if you apply this transformation to X, you just get T of X plus T times E, and that's T of X by linearity plus T times T of E. But T of E is lambda E. So you get T lambda E. So you're now flowing by time T lambda E. So to put it differently, if you move the T over to this side, when you conjugate this flow by T, you accelerate it. It goes faster because you have this power of lambda here. And in fact, if you were to conjugate it n times, it would go much faster, exponentially faster. You get a high power of lambda in front of the H. And that's just an algebraic way of writing down this fact that as you iterate the ball, it grows exponentially fast along the eigendirection. So what kind of group is generated by T and H? There's only a few adjectives that apply to general abstract groups. So what adjective would apply here? Anybody? Don't forget, I'm willing to cold call people.
Solvable.
Yes, who said that? Okay, Carl saved the day for everyone. I can always do that. Yes, it generates a solvable group. It's not quite Abelian, right? If this lambda to the n were 1, it would say these two transformations commute. But instead, it generates a solvable group. So conjugation by T sends this subgroup into itself. In other words, H generates a normal subgroup of the group generated by T and H. So in fact, we have an exact sequence. 0 goes to R, which is the group generated by HT, goes to the group generated by T and HT, goes to Z. where Z is just the group generated by T. Okay, so it's a solvable group, and the behavior of this solvability is a crucial feature. When we can find that in dynamics, it often gives us a leg up. Okay, so now I'm going to give the proof that T is mixing. Okay, so let's suppose we have F and G in L2 of X, and that they both have mean 0. So remember, what we want to prove is we want to prove that, say, T to the n F G tends to 0. Okay, so the first thing we do is we write T to the n F G equals, I'm going to put the F on the other side, it's T to the minus mg. Oh, let me make a little remark about these maps considered as operators. The adjoint of T is T inverse, right? Because T is a unitary operator. The adjoint of HT is H minus T. But what's the adjoint of ST? ST was our averaging operator, and it averaged from minus T to T. So when you take its adjoint, it averages from T to minus T, but that comes out to be the same. So this is self-adjoint. And the other thing I want to remind you is that continuous functions are dense in L2. And if you move a continuous function back and forth very slightly, it doesn't move very much in L2. That's what it's uniformly continuous. But by the same token, if you take any function in L2 and you slide it back and forth a little bit in average, you barely change the function. So what I'm going to do, and this is the main idea in the proof, is I'm going to write this as approximately equal to ST F T to the minus mg, where T is very small. So this is equal to within a factor of, say, 1 plus or minus epsilon, as long as T is very small. Now just jiggle the function f a little. But now watch. So if we now write this as, let's move the T back over to the other side. So now we have T to the n ST F inner product with G. And because of the fact that T to the n conjugates HT and accelerates the flow by a factor of lambda n, it also accelerates the averaging process. So this is the same thing as, and now I'm probably getting myself a little bit confused. Okay, I guess this is going to be okay. It's a little less obvious than I wanted. Maybe we'll get this. Okay, so this is, sorry. Sorry, let me move the ST, I see. Let me change some ends here, just to make it a little bit more palatable. So, yeah, let me just try to study this inner product, the f of f, the inner product between f and t to the n of g. Okay, so that's approximately equal to let me see how I want to do this. I'm just getting the ST on the wrong side. Sorry about that. Okay, so let's continue from here. And now I'm going to put the ST on the other side. I'm sorry, I've confused my right and lefts. Okay, let me say what it is I want to use, and then we'll give the proof. Okay, so what we note is that F is approximately equal to STF, and that S lambda to the n F TF tends to 0 in L2. So I wanted to get to something where I have an S lambda to the n in front of F. Yeah, so let me just see how I can do that here. So if I put a t to the minus n here and a t to the n here, then this equation gives me, right, so sorry, I needed to use a slightly different identity. What I want to use is the identity that t to the minus n, s lambda to the nt, is equal to st t to the n. T to the minus n. Okay, so let me just write down something related to that. So what we find is that t to the minus n, yeah, right. So f t to the ng, I'm still getting things backwards. Sorry. Okay. So if we look at minus t to the n f, this is approximately minus t to the n f g. This is approximately equal to t to the minus n f st of g with t small. But this is equal to st, t to the minus n f, inner product with g, moving the averaging over to the other side. And then using this equation, that's equal to t to the minus n s lambda to the nt applied to f, inner product with g. Okay, so now the essential point here is that by the ergodic theorem, since f has average 0, this guy tends to 0 in L2. But t is a unitary operator. So when you apply it to a vector that's tending to 0, well, it preserves its norm. So this whole thing tends to 0. And g was just a fixed vector. And so this whole thing tends to 0. And that's what we need to prove for mixing. Okay, sorry for that little confusion. But again, the idea is you use the fact that for small t, f is equal to a small average, but then when you interchange the actions of t and f, small averages become big averages, and that's enough to establish mixing. Okay, so that is the Hopf proof of ergodicity, of mixing of the torus automorphism. Now, why is this better than, say, using a proof by Fourier analysis? Well, there's a couple of reasons. One is that this proof will generalize to our analysis of the geodesic flow on a hyperbolic surface. And the group theory, the harmonic analysis will be much more complicated. It's a tremendous pain to try to do eigenfunctions of the Laplacian or something like that on, say, a hyperbolic surface. But this simple argument about solvable groups will go through in exactly the same way when we study the geodesic flow. But another reason, perhaps even more important, is that this proof is stable under smooth perturbations. If you take this transformation T and you move it a little bit in the C infinity topology, you get a map that does not respect in any way the group structure on X. But these foliations persist. And the reason they persist is that the derivatives change only slightly, and so they continue to have real spectra. And so for the perturbed map, you get a family of foliations going in both directions. You can flow along those leaves just as before. You can prove the ergodicity of that flow using some simple facts about the foliation. And therefore, you prove that not only is T mixing, but smooth perturbations of T that continue to preserve area are also mixing. That famous breakthrough due to Anosov showed that there are certain so-called structurally stable maps that in the smooth topology continue to enjoy nearby the same properties as their linear models. Okay, so any questions on the Hopf argument or the ergodic theory we've done to date? Okay, so just for a little refreshment, I want to change pace in a simple way. So let me go to this. Okay, so we're moving on to hyperbolic surfaces, and this is not hard at all, but I just want people to gather in small groups for 5 or 6 minutes. Again, introduce yourselves, and then solve this problem. Now, what is this problem? This is the classic utility problem. You have 3 homes and 3 utilities, and you have to construct utility lines that go from every home to every utility, but they're not allowed to cross themselves. Well, it's a famous fact that you can't do that by a planar graph. Well, if you look at this picture carefully, you'll see that you have a couple of other options. And so your goal in your breakout room is to draw a solution to the utility problem in this picture. And it's good if you can do it on an iPad, that will be nice. If you can do it on a piece of paper, that's also fine. You can certainly copy the diagram or give an indication of it. And so again, elect a reporter, and then we'll check back in and share our solutions. Okay, so I'm going to go to breakout rooms, if I can remember how to do that. And we'll reconvene in just 5 or 10 minutes. And this should be an easy project. Okay. Oh.
And my breakout room only has myself, one person.
Oh, sorry. Who said that?
It's Karina.
What breakout room are you in?
Breakout room 1.
So I show 3 people joined there. Oh, you
Oh.
had Mary Stilo, Bin Kale, and Jonathan Boretsky should be there.
Let me try again. Maybe
Okay.
it's something weird with my Zoom.
Oh, somebody asked for help. Okay, let me. In fact, sitting inside of complex geometry on the plane. So what's inside of here? What's the conformal geometry of the Riemann sphere? So we look at the Riemann sphere, we look at the group of automorphisms that preserve the complex structure. And this group is almost the same as the group SL2C. Namely, a 2x2 matrix acts by the Mobius transformation AZ plus B over CZ plus D. So conformal geometry, which is we will use all the time, the Mobius transformations acting on the sphere, will turn out to receive or contain inside of it copies of something that's almost SO3 and copies of something that's almost SO21. And those will be, it will therefore be the receptacle for these different kinds of geometry. It can even contain Euclidean geometry appropriately considered. Small remark, of course, when you deal with Mobius transformations, these two groups are not quite isomorphic. And the reason is that minus Z over minus 1 is Z. So there's a small kernel here, which is plus or minus the identity. And often for convenience, I will work in this group Although technically the automorphisms of the Riemann sphere are not this group, they're its quotient by that Z mod 2. And so this is isomorphic to what's called PSL2C, the projective special linear group, just mod out by scaling. Okay, so here's my model for spherical geometry. I'm going to take my space to be the Riemann sphere. And then on the Riemann sphere, I'm going to introduce a metric. And this metric will be the Euclidean metric scaled by a factor of 2 over 1 plus the absolute value of z squared. And now, what's of critical importance in the discussion of a space like this is the isometry group of the space, the symmetry group of the Riemann sphere that preserves this metric. Now, if you preserve a metric, you have to preserve the conformal structure. So the symmetry group will be a subgroup of SL2C. So what does the symmetry group look like inside of the group of Mobius transformations? It looks like the group SU2. So SU2 is essentially the isometry group of the Riemann sphere with respect to this metric. And this metric turns out to have constant curvature plus 1. Now, what is SU2? SU2 is just like the orthogonal groups we've been considering, but in the Hermitian case, rather than in the real case. It has to do with Hermitian interproducts on complex vector spaces. And to see the connection, note that we can regard the Riemann sphere as the projectivization of C2. And then the action of SL2C just comes from the obvious linear action of SL2C on the underlying vector space. Now, if we introduce more structure to C2, then we'll get a subgroup here that preserves that additional structure. So what we do is we add on to C2, we introduce the obvious inner product, ZW, is Z1 W1 bar plus C2 W2 bar. So this is a Hermitian inner product as opposed to a real inner product. And there's a classification theorem for Hermitian inner products that's just almost exactly the same as for real inner products. Namely, a Hermitian inner product has a signature. It can be represented in appropriate coordinates by some elements on the identity and a multiple of the identity, and minus a multiple of an identity of a different rank. So this is the case where we're on C2. We have 2 positive coordinates and 0 negative coordinates. And what's SU2? It's just the subgroup of automorphisms of C2 that preserve this inner product. It's the unitary group. But differently, we have a 2-dimensional Hilbert space. We look at the automorphisms of that Hilbert space that preserve the inner product and have determinant 1. That's just a convenience to make the group slightly smaller. Okay, and now what does this group actually look like in real life? So the elements of SU2 will be a special set of matrices, and they're those of the form AB minus B bar, A bar, subject, of course, to the condition that the determinant is 1, which just becomes A squared plus B squared equals 1. Okay, so why are these the orthogonal group? You see, you start with a standard basis, 2 orthonormal vectors, and now you can move them to any other 2 orthonormal vectors by a linear transformation. Those are the isometries. So the image of the first vector, let me think in terms of rows, in terms of columns, this vector here has to be orthogonal to this vector here, and it has to have length 1. So for the length of this to be 1 is to say A squared plus B squared is 1. And then if you take the inner product in this form here, you'll see that between these two, you get AB minus BA, which is 0. So that explains why this is what the group SU2 looks like. And what you'll notice is that SU2 can be itself, it only depends on 2 variables. complex variables A and B, and it can be thought of, therefore, as a subset of C2 in its own right. And what subset is it? It's just a unit sphere. So SU2 as a group is isomorphic to S3. So in particular, it's a simply connected group, nicely sits inside of SL2C, and you can verify that it's the transformations that preserve this metric. Moreover, since any vector can be the first element of a basis, this group acts transitively on the sphere, and therefore the sphere has constant curvature because it has to have the same curvature at points that are related by an isometry. One can then check that the group comes out to be right. And finally, I should say that, of course, this geometry, we call this model 1, can be related to the geometry model 2. And model 2 is you make your space just to be the unit sphere in R3. So it's the set of x, y, z. So it's an x squared plus y squared plus z squared equals 1. And then its metric is the induced metric from R3. And finally, the isometry group, at least if we require that orientations are preserved, is this group SO3. So we now have two models for spherical geometry. One of them involves an inner product on three-dimensional space. One of them involves an inner product of two-dimensional complex space. And there's a lot of interesting stuff going on in the relationship between these two. For example, this guy is not quite equal to the isometry group because, as usual, plus or minus the identity goes to the identity element here. This guy, SO3, is equal to the orientation preserving isometry group. So there's a map that goes from SU2 to SO3, and this is a 2-to-1 covering map. This is at the actual isometry group. The kernel is plus or minus the identity. And so this space is isomorphic to RP3, since it's doubly covered by the sphere. Okay, so let me quickly conclude by saying one of the main features of spherical geometry that will have an analog in hyperbolic geometry, in fact, everything that I'm saying today will have an analog in the hyperbolic case. I'm doing the spherical case just because it's sort of more familiar, easier to visualize inside of the Euclidean space where we live. The final thing I want to say is the behavior of spherical triangles. So on the sphere, the geodesics turn out to be the great circles. And as usual, when you have two great circles, they have to intersect. And when they intersect, they have an angle. And if you take three great circles, then they typically bound a triangle. In fact, they bound two triangles, one of which is antipodal to the other. And as you can kind of intuit just by looking at the diagram, the angles of this triangle have a sum which is not pi as it would be in flat space, but which is greater than pi. And the beautiful fact, which I'll indicate the proof of, is that the area of T is equal to what's called the angle defect. So you add up what the angles are, and then you subtract off what they should be in flat space, in Euclidean space. And the end result is the area. So for example, if you take an orange slice of the sphere, that is, if you take one quadrant in the northern hemisphere, the area of this is, you have the area of the whole sphere, 4 pi, then you divide by 8, so you get pi over 2, and its internal angles are all 90 degrees. So you get that in this case, the angles are pi over 2 times 3, you subtract out pi, which is what they should be, and you get the area, which is pi over 2. Okay, so in a little bit over time, let me just conclude by indicating how you might prove this Gauss-Bonnet area theorem for triangles. What you can do is you can start with a case which is really obvious, which is the case of a line beginning and ending at the north and south poles, together with another line, another geodesic that does the same. So two great circles. Two great circles form what's called a loon. And the loon is uniquely determined by its two angles, and these angles have to be the same by obvious symmetry of the sphere. You could ask yourself, what's the area of a loon? Well, it's pretty easy to figure out what it should be, because a loon where alpha is 2 pi would just be the whole sphere. So it has to be something that comes out to be 2 pi for the whole sphere. In fact, the area of a loon is equal to its angle defect. Now, what's the angle defect? The angle defect is the sum of the angles, which is alpha plus alpha, minus what they should be in Euclidean space. But in Euclidean space, if you have a bigon, that is two lines that begin and end at the same points, the angles are both 0. So the sum in Euclidean space is 0, and you just get 2 alpha. So at first, this formula that area equals angle defect works for arbitrary polygons. And second, you can deduce the general case by starting with the case of a bigon. Okay, so next time I'll wrap up this brief introduction to spherical geometry and then go on to hyperbolic geometry of the plane. And as usual, I'll hang out in the Zoom room for a bit. Thanks.